So our today's discussion will be about this spanning tree. Okay, so we're discussing the graphs, right? So what is graph? We all know that if we have some vertices, then we can create a graph. How? By connecting those graphs, right? Suppose this is a graph with four vertices, A, B, C, and D. How many vertices or nodes are here? Four nodes. And if we can represent graph as G, then this graph is actually set of vertices and set of edges. G equals to V and E, where V is the number of or the sequence of vertices and E equals to edges. Okay, so suppose this is a connected graph, so we can take some edges from A to B, A to D, D to C, and C to B. And we already learned about different types of graphs, right? So now look at the structure of this graph. Is this a simple graph, or can we call it connected graph? Which one it is? Each type of graph, each of them have some specific characteristics, right? And in this graph we can see that each node or each vertex is connected with at least one more vertices of this graph. Or in another sense, we can say that there is an edge between every two nodes. Between A and B, there is an edge. Between B and C, C and D, and D and A. So what kind of graph it is? It is a connected graph, right? So if it is a connected graph, then what are the characteristics of this graph? One characteristic is this connected graph cannot have any loop. What is loop? If the starting point and the destination points are same, that edge is called loop. Okay, so this connected graph cannot have any loop, as well as it cannot have any parallel edges. What is parallel edge? If between any two nodes, then if the number of edges is more than one, those edges are called parallel edges, right? So a connected graph cannot have any parallel edge, or it cannot have any loop, right? So there are some other types of graph, that is multi-graph. What is multi-graph? If there are some loops or cycles or parallel edges, we can call it multi-graph. What about weighted graph? If we are assigning some values here to each of these edges, that will be called weighted graph. So now how we can create the spanning tree from this graph, or what is actually spanning tree? Do we know what is a tree graph? What is tree graph? There is one more type of graph which is called tree graph, isn't it? What is the characteristic of that tree graph? The characteristic of tree graph is if the number of node is n, then in a tree graph we can have how many edges? N minus one number of edges. That is tree graph. And another characteristic is in a tree graph we cannot assign any loop, or we cannot have, or the graph cannot have any parallel edges. That is a characteristic of a tree graph. So if it is a graph, then how we can create the spanning tree? How we can create the tree graph? Look at this graph. How many vertices are here? V equals to A, B, C, D. So there are four vertices. And the number of edges is also 4. So how to create this spanning tree? If we remove some edges from this graph, we can create a spanning tree. So how many edges we can remove? A spanning tree is a subgraph. We can call it subgraph where all the nodes will be same. Suppose this is our spanning tree. This is initially empty. So we can take all the nodes from this graph. So the graph has 4 nodes. We can have exactly these 4 nodes in the spanning tree. But one difference is here in this spanning tree, the number of edges will be less than to this graph. In this graph, we used how many edges? 4 edges. So in this spanning tree, the number of edges will be vertex minus 1. How many vertices are here? 4 vertices. So the number of edges will be n minus 1 or v minus 1, that is 3. So now if we want, we can remove any edges from this graph. Suppose we have taken only 3 edges, that is this one, A to D, A to B, and B to C. So in this tree or in this graph, how many vertices we have taken? 4 vertices, A, B, C, D. Exactly the same number of vertices we have taken from this graph. And how many edges are here? 3 edges. That is, the number of edges will be always 1 less than the number of vertex. So we can call it a spanning tree. Is it clear what is spanning tree? Spanning tree is a subgraph where the number of vertices will be equal to the number of vertices in the graph, and the number of edge is one less than the number of vertices of the graph. Is it clear?
Yes, ma'am.
So now from a complete tree or from a connected tree, how many spanning tree we can have? We can have several spanning tree. Look at this. If we remove this edge now, suppose these are our four vertices A, B. In spanning tree, the number of vertices will be same. There are four vertices A, B, C, D, and now we are just taking three edges. This one A to B, B to C, and another one is C to B. So this is another spanning tree. That means from one connected tree, we can create how many spanning tree? So many, right? And now, so if all these structures can be considered as spanning tree, then how we can calculate, how we can find out which one is the minimum spanning tree? Minimum spanning tree. So for finding out the minimum spanning tree, at first we have to assign some age value. So these are our ages. So here, if we assign some values like this, 1, 2, 3, and 4, and after taking some spanning tree, look at this. How many ages we have taken? 3 ages, and their values are 4, 1, 2. Now, if we calculate the total weight of this graph, of this spanning tree, then what will be the value? 4 plus 1, 5. 5 plus 3 equals to 7. What about this spanning tree? The age value is 4, this is 3, and it is 2. So 4 plus 3 equals to 7, 7 plus 3 equals to 9. If we create another spanning tree, suppose these are our ages, A, B, and C, D, and we just took this 3H. So this is another spanning tree, and their weights are 1, 2, 3. Now the total weight of this spanning tree is 1 plus 2, that is 3. 3 plus 3 equals to 6. So which one is minimum spanning tree? Obviously the tree with the minimal weight. So this is minimum spanning tree. From a graph, we can create several spanning tree, and if the weights value are different, here we have taken some unique weight value, unique weights. Okay, so at that time we can have only one minimum spanning tree, this one. Is it clear how to find out the minimum spanning tree?
Yes, ma'am.
Okay, and look at this. The graph that will be given, that graph can have several vertices, right? 7, 8, 10, 15. So is it possible for us to test every time to create several spanning trees to find out which one will provide the minimum weight? It's not possible, right? Or it will be, time consuming, right? So here, if we want to find out which one is the minimum spanning tree, we can apply two algorithms here. One algorithm is called Kruskal algorithm, and another is Prim's algorithm. So we'll apply these two algorithms for finding out the minimum spanning tree. But before that, just look at this graph. If it is a connected graph, how it can make it complete graph? What is the definition of complete graph? In a complete graph, each of these vertices will be connected with all the other vertices. So here, A will be connected with C, and we can draw another edge from D to B. So is it a complete graph? Yes. This is a complete graph, and we know that in a complete graph, the number of edges is n into n minus 1 divided by 2. So here the number of edge is 6. Okay, so from a complete tree, we can have how many spanning tree? N to the power n minus 2 number of spanning tree. There are some, or we can find out some characteristics of spanning tree now. The first one is we can take any graph. Okay, the graph can be a connected graph, it can be a simple graph, it can be a multi-graph. But at that time, how many spanning tree can create? Several, right? But if the graph is complete graph, then the number of spanning tree will be n to the power n minus 2. So here n equals to 4. That means from this graph, we can create how many spanning tree? 4 to the power 4 minus 2, that is 4 square equals to 16. So you can try it. From this graph, you can create how many spanning trees? 16 spanning tree. But the minimum spanning tree will be only 1. If the weights value are unique, look at this here, we didn't use the same weights for two ages. The weight values are 1, 2, 3, 4. all these weights are different. So at that time, you can have only one minimum spanning tree. If you are taking several, I mean same weights, that is 3, 3 to 1, at that time maybe the minimum spanning tree can be 2 or 3. But for unique values, the minimum spanning tree will be only 1. Clear?
Yes, ma'am.
Okay. So now we'll apply this Kruskal algorithm for finding out the minimum spanning tree. So suppose a tree is given, this graph is a weighted graph. So the first vertex is A, then B, C, D, and E. So in this graph, the number of vertices are 5. And these are some edges, A, B to D, D to E, C to E, then A to C, B to C, and B to E. Okay, so what type of graph it is? Is it big graph? No. We can call it a connected graph. Okay, and from this connected graph, we can create so many spanning trees. So now we can assign some weights. So the weight of this edge is 35. For this edge, 10, 30, 10, 15, 20, 25. And for this edge, the weight is 40. Okay. So now in this graph, if G is a graph, then how many vertices this graph has? 5 vertices. A, B, C, D, and E. And how many edges are here? 7 edges. 1, 2, 3, 4, 5, 6, 7. And all the weights of these edges are unique. Right. So if we want to apply the Kruskal algorithm, and what is the functionality of, or why we're using this Kruskal algorithm? Why we're using it? For finding out the minimum spanning tree. Okay, so suppose the graph can have some loops. So this is a loop in this node E, and the graph can have some parallel edges. So the first step will be remove all the loops and all the parallel edges from this graph. If we want to create a minimum spanning tree from this graph, what will be our first step? The first step is remove all the loops and all these parallel edges. So now this edge can also have another weight. Suppose its weight is 45, and this is another edge and its weight is 5. Okay, so we can simply remove this loop from this graph with its weight. And now between these two nodes B and D, how many edges we have taken? 2 edges, 10 and 45. So which one should be removed? There are 2 edges between B and D, and their weights are 10 and 45, right? So which edge will be removed? The edge with the maximum weight. So this one will be removed. That is the first step of Kruskal algorithm. Remove all the loops and all the parallel edges. Now what is the next step? The next step is we can create a list, or we can store all the edges in ascending order. That means at first we will take an edge with minimum weight. So which edge has a minimum weight? Here, BD. So at first we will store the edge with minimum weight. So here the weight of BD is 10. We're storing it in ascending order. So now the next one will be 15. That is CE. The next edge is CE and its weight is 15. Which one will be the next? BE, right? And for BE the weight is 20. And the next one is this one, BC. These are, I mean, the graph is undirected graph, right? So you can write BC or CB. And its weight is 25. And the next one is 30. So DE with the weight 30. After that, AB. And the last one is this AC. So now we have organized all the edges in ascending order. Okay, so what is the next step? The next step is now we have to create the minimum spanning tree. So how to create that minimum spanning tree? Now we are going to take the edges from this list. Minimum spanning tree is a subgraph, right? Where the number of vertices will be same. So how many vertices we can take in that minimum spanning tree, 5 vertices. So this is A, B, D, C, and E. So these are our 5 vertices. And what about the number of edges? The number of edges 1 less than the number of vertices. That means in this minimum spanning tree we have how many edges? Only 4 edges. 5 minus 1 equals to 4. So which 4 edges will be chosen from these 7 edges? It depends on their weight, as well as in this spanning tree we cannot create any loop, or we cannot create any, or we cannot assign any parallel edges, or you cannot have any cycles. Okay, so now at first we will take this one, BD. So this is the vertex B and this is D. We can create an edge between B and D. And what is its weight value? 10. So the first edge is BD. So after taking the first edge, now take the next one, CE. So this is the node C. We can draw an edge between C and D, and its weight value is 15. Okay. Then the next one is BE. So this is B and this vertex is E, and its weight value is 20. And then the next one, so the next one is BC. Look at this. Can we take this edge BC? We can't take it. Why not? Because if we take this edge at that time, we are creating some cycles here. What is cycle? If the starting node and the end node is same, that is called a cycle. Look at this. After taking this vertex, this edge between B and C, we are creating a cycle B. But minimum spanning tree cannot have any cycle. So this edge will be ignored. We cannot take the edge BC. Clear why we are ignoring that edge? Because after adding it, it will create a cycle. Okay. Now the next edge is D. So can we take that edge D? No. Why not? Because it will create a loop. Sorry, it will create a cycle. That's why it will be removed. Okay. Now the next edge is AB. So can you take that edge? Yes. So this is AB with the weight 35. Okay, and the next one is AC. Can you take that edge AC? No. Why not? Because look at this. It's creating a cycle ACEBA. That's why we'll ignore that edge AC. Okay, so now look at this spanning tree. The number of vertices are 5, but the number of edges is 4. And if we count the total weight of this graph, then the weight will be 35 plus 10, 45, 45 plus 20, 65, plus 15, 80. So this is the minimum spanning tree. If you want, you can create some other subgraph, and at that time you get the weight more than 80. Clear what is Kruskal algorithm? We are using this algorithm for finding out the minimum spanning tree. Okay, so the first step is we have to remove all the parallel edges or all these loops, right? And then store all these edges according to their weights in ascending order. And now we can add the edge in this minimum spanning tree. How? We just have to notice that whether, if after adding any edge, if it's creating any cycle, then you have to delete it. Otherwise, you can take the edges. Is it clear what is Kruskal algorithm?
Yes, ma'am.
What about the others? Is it clear?
Yes, ma'am, clear.
Okay, so we just need to consider these three things. The first one is in a minimum or in a spanning tree, the number of vertex will be equal to the number of vertex of the given graph. The number of edges will be 1 less than the number of vertices of that graph. And we cannot assign any edges where it will create some cycles. These are three main characteristics of spanning tree. And in minimum spanning tree, after adding all these edges, the value will be minimum. So this is Kruskal algorithm. Now the next one is Prim's algorithm. So we can take another graph with 6 vertices. So the vertices are A, B, C, D, E, and F. And These are some edges from A to B, E to D, D to F, F to E, E to C, and one edge from B to C, C to D, and one is D to E. Okay, so this is a connected graph. Now we can add some bits. 6, 3, 2, 5, 3, 4, 2, 3, and 5. Okay. So now we'll use the Prim's algorithm. In the previous one, in Kruskal algorithm, we deleted all the loops and all the parallel edges. So in this graph also, there can be some parallel edges or there can be some loops. So the first step is just like the Kruskal's algorithm. Remove all the parallel edges and the loops. Okay, so what is the next step? In Kruskal algorithm, we organized the edges in ascending order, but here we'll not do that. We'll just take one vertex from this graph. What is spanning tree? If we want to create a minimum spanning tree, then the number of vertex will be same. How many vertex we can take here? 6 vertices. A, B, C, D, E, F. But the number of edge will be 6 minus 1, that is 5. And in minimum spanning tree, the total weight will be minimum, right? So now how we can choose the edges from this graph? So in Prim's algorithm, we can take any vertex. It can be B, D, or C. Suppose we are taking the first one, that is A. A is the first vertex. So now in Prim's algorithm, we have to find out the adjacent vertices of A. So which nodes are the adjacent node of A? Only B and C, isn't it? Look at this graph. Which vertices are adjacent vertices of A? B and C, because there are two edges from A to B and from A to C. But in Prim's algorithm, we cannot take more than one edge at a time. How we can choose one edge between these two? We will take that edge with the minimum weight. So between these two edges, which one has the minimum weight? This one, AC. So we'll take this edge from A to C. So our next vertex will be C, and its weight is 3. Okay, so now we're here. After getting C, what is the next step? The next step is find out all the adjacent vertices of C. So C has 4 adjacent vertices A, but A is already taken. Then B, D, another is E. So these 3, we have already added that edge in this minimum spanning tree, right? So the unvisited edges are this one, C to B, C to D, C to E, right? So now among those 3 edges, again, we have to find out which one has the minimum weight.
B.
So which one? This C to B. But here another thing is when we are comparing these edges, we can't forget about the previous one. Our previous vertex was A, and this A has 2 neighboring nodes, but we have taken only one. So now along with this, C has 3 adjacent vertices. So when we are comparing these 3 edges, at that time you have to compare this one also. Right, so now there are 4 unvisited edges, that is 6 with weight 6, 2, 3, 4. So which edge has the minimum weight? This one, C to B. So we'll take B as the next vertex. So B is the next vertex and its weight is this, edge weight is 2. Okay. Now the next step is find out the adjacent vertex of B. So B has how many adjacent vertices? 3. That is B to C, but it's already taken. Then B to D, and another is B to A. So there are 3 vertices, or we can consider this vertex or this edge as the vertex of A, right? So how many edges are here? 3 edges. One is 5, another is 2. This is already visited. So now we have to make the comparison between these 2 edges. One is 5 and another is 6. So which one will take now?
5.
Very good, 5, right? And this edge is between B and D. So our next vertex will be D. The weight is 5. Okay, so we have taken this edge also. Now the next step is find out the adjacent vertices of D. How many adjacent vertices it has? 4. D to B, or B, C, E, and F. but this edge is already taken, so we have to compare this 3 edge with the weights 3 to 3 with this one, with this edge from A to B, right? So among those 4 edges, now which one we should take? The
E.
one with the minimum weight, this one, D to E. So next vertex will be E. And what about its weight? Its weight is 2. Okay, so now the current node is E, and it has how many adjacent vertices? 3. C, D, and F, but D is already taken. So now we have to compare this 2H with weights 4 and 5, and one more edges is here, 6. We didn't take it. And what about D? D has 4 vertices, isn't it? How many adjacent vertices D has? 4. But we took only one vertex, that is this one, right? So now the next step is we have to compare all the edges that is related with the vertex E as well as D and A. So how many edges are here? 6, 3, then 4 and 5, right? So now which one will be the next edge or next vertex? Our current vertex is E. Look at this. Our current vertex is E, and it has how many unvisited vertices? 2. One is from E to C, and another is from E to F, and their weights are 4 and 5. But our previous vertex was D, and D has some other adjacent vertices, that is C and F, and their weights value were 3 and 3, right? And A has one more edge between A and B, and the edge weight is 6. So now we have to compare how many edges? 1, 2, 3, 4, and 5 edges. And these 2 edge has the same weight, so we can just take 1. So which one will be the next edge?
4, but if we take 4,
Can we take this one? No, we can't take this edge because it will create a cycle.
yes ma'am, then 5.
So we should take D to F. And another thing is we cannot take a node twice. If we add one edges between D and C, at that time we're visiting this node twice. Okay, so ignore this edge. Now this edge weight is 3. Look at this graph. Look at this minimum spanning. Look at the spanning tree. The number of vertices are 6, and it's E, A, B, C, D, E, F. And how many edges we have taken? 5 edges. So this graph, or we can call this graph spanning tree. So is it minimum spanning tree? Now add all the weights. 3 plus 2, 5, 5 plus 5, 10, 10 plus 2, 12, 12 plus 3 is 15. So this is the minimum spanning tree. And how we got this minimum spanning tree? By applying this Prim's algorithm. What is Prim's algorithm? In this approach, in Prim's algorithm, the first step will be the removal of all parallel edges and loops, and then we can just start with any node, any vertex of this graph. But after that, you have to find out the adjacent vertices of that vertex, and then compare all the edges. Okay, and then take the minimum weight edge. So in this way, we can take all the vertices from this graph, and how many edges we can take? 1 less than the number of vertices. Clear?
Yes ma'am. And there had a question. When
Yes.
we are using the Google map, does this algorithm use to find out the destination in the shorter way?
No, at that time we have to use shortest path algorithm. We'll discuss those algorithms in our next class.
Okay ma'am.
Okay.
Yes ma'am.
So our next topic will be shortest path. How to apply the Warshall's algorithm or DJ Custer's algorithm for finding out the shortest path. Here, by using these 2 algorithms, we just created some spanning trees. I hope it's clear to you. But still, if you have confusion, you can ask me any question. Any confusion in this 2 algorithm? The first one was Kruskal's algorithm, and this is Prim's algorithm. The main difference is in Kruskal algorithm, we have to create the list with all the edges in ascending order, but here we can just take any nodes from the graph, and then we have to take every time we can take only one edge with minimum weight. This is Prim's algorithm. Is it clear?
Yes ma'am.
Okay, so you can do one thing. I'm giving you another graph. So apply Prim's algorithm and Kruskal algorithm to find out the minimum spanning tree. Okay, so this is a graph with six vertices and the edges are nine. Okay, so you have to find out the minimum spanning tree by using two algorithms. The first one is Kruskal's algorithm, and number two, Prim's algorithm. Hello? Hello? Hello?
Yes, ma'am.
Okay. The first one is Kruskal's algorithm. Okay, first tell me, did you get the same graph from these two algorithms, Kruskal and Prim's? Hello?
Didn't get you clearly. Could you say that again?
My question is, you already applied these two algorithms, right? So did you get the same spanning tree from those two algorithms?
No, ma'am.
Why not?
Oh, yes, ma'am. It does.
Yes, the spanning tree should be same, right?
A to B, B
So
to yes,
which edges you have taken? The vertices will be same, right? A, B, C, this is D actually. C, and it's, okay. So which one is your first edge?
A to B,
A to B, okay, this one. And then
B to E,
B to
E,
B to E, okay.
then E to
And
D,
then, very good, E to D,
then D to F,
D to F,
and there has E to C.
very good, E to C. So this is the minimum spanning tree. And look at this here. The number of edges is 6 minus 1, that is 5. And is there any cycles here? No. So this is the minimum spanning tree. Clear?
Yes, ma'am.
I'm not getting the responses from the others. Is it clear? The minimum spanning tree?
Yes, ma'am.
Yes. Okay. So in the next class, we will discuss about some other algorithms, such as DJ Castra or Warshall's algorithm.